research. Thanks for coming tonight. Couple of reminders. First off, if you haven't renewed IEEE renewal, you're coming up on your last chances to keep it renewed for this coming year. So please do that if you haven't already done that. And later this year, we're going to be holding elections for the board. If you're interested in serving on the board, please feel free to reach out to anyone who's already on the board. You can go to our website, r4.ieee.org/smn, and find contact info on there if nowhere else. And I just wanted to thank everyone again for coming this month. Right now, I'm going to introduce our speaker. Dr. Pailang Liu is a research fellow at Mayo Clinic, specializing in AI-driven methodologies to advance pathology practice by developing techniques in pathology image analysis, knowledge representation, and graph-based learning. He aims to leverage his specialized AI expertise and deep understanding of pathology workflows to create solutions that streamline disease diagnosis, inform clinical decisions, and foster sustainable healthcare practices, ultimately ensuring maximum benefit for both patients and pathologists. So please give a hand and welcome Dr. Liu.
Good evening. It's a great honor and pleasure to be invited here to give a talk. Today I'm going to talk about PathoGraph, a graph-based method for standardized representation of pathology knowledge. I'll spend around 40 minutes to finish the talk and leave 20 minutes for question and discussion. Now let's begin. Before starting my talk, please allow me to briefly introduce myself. I come from Xi'an, a historical city in China, and I received all of my education from Xi'an Zhongnong University. And Xi'an is a city with a history spanning over 3,000 years and is world famous for the terracotta warriors, the tomb of China's first emperor, former US President Ronald Reagan and Bill Clinton both visited this place. There's a well-known saying in China: if you want to see modern China, visit Beijing. If you want to see China in 100 years, go to, if you want to see modern China, visit Shanghai. If you want to know China in 100 years, go to Beijing. But if you want to see China from 1,000 years ago, you should go to Xi'an. And the 3,000-year history has cultivated a rich food culture, which has inspired my passion for cooking. So if I hadn't come to Mayo to work, I would probably running a restaurant right now. So my signature dish is a biang noodle, one of the most iconic foods from Xi'an, and also among the most popular noodle dish in China. Here are the two pictures of noodles I made. Since coming to Mayo, I've frequently cooked various Chinese.
It looks really good.
Oh, okay. And I have prepared a few further details that this is a belt-like noodles and topped with stir-fried pork belly, seasoned with vinegar and stir-fried tomato and eggs, and also seasoned with the crushed red peppers, sizzling red oil. So it would not only satisfy your stomach, but also your soul. So since I joined Mayo Clinic, I frequently cook various Chinese dishes, not only to survive the cold winter of Minnesota, but also to bring taste of home to Rochester. So if anyone is interested, I would be more than happy to share my recipes. Let's get back to my research. So my research started in my sophomore year. During that time, I developed a method for recommending locations of interest to social media users. And during my master year, my research focus is on biomedical text mining. Then since 2019, my research focus shifted to AI in pathology with a focus in knowledge representation. And this project is collaborated with pathologists at Mayo Clinic. So let's begin with the research background. The field of pathology has generated vast data resources primarily in the modalities of hemotoxylin, eosin slides, immunohistochemical slides, and pathology reports. So these resources encapsulate critical pathology knowledge about diseases. Such information is essential for advancing data-driven biomedical research and clinical practice. Specifically, pathology knowledge in HE slides are mainly about the composition of diseased tissues. And there are pathological characteristics at the cellular and tissue levels. In other words, histopathological phenotypes and the cytopathological phenotypes. In IHC slide, the focus is on immunophenotypes, which reveal the protein level characteristics of diseased tissues or cells. In pathology reports, the knowledge is about diagnostic expertise of pathologists, such as their analysis of phenotypic characteristics in the form of natural language description of the phenotypic morphology. And there are diagnostic approaches, which is often involve differential diagnostic processes. The figure in the right provides a schematic representation of this diagnostic process. In this process, a pathologist would use phenotypes as a basis for diagnosis. The purple rounded rectangle here refer to phenotypes from HE slides, and the orange ones refer to immunophenotypes from IHE slides, and the blue ones refer to diagnostic possibilities considered in this process. So based on these phenotypes, the pathologist considers and excludes multiple diagnostic possibilities and ultimately arrive at the definitive diagnostic conclusions. Despite its value for advancing data-driven biomedical research and clinical practice, pathology knowledge is hidden within both textual data and images, which is not conducive to its computational utilization. So for example, the rhabdoid cell, which is a malignant kidney tumor cell showing in this figure, is described as large, eosinophilic, irregular shaped, while only professionals understand what qualities these descriptive terms refer to. So as a result, computational methods struggle to fully understand and analyze pathology data, as pathology knowledge is implicitly captured in the data modalities, making it less accessible for computational analysis. Additionally, pathology knowledge is fragmented across modalities. For instance, the figure illustrates how the components of a diagnostic process, detailed in the previous slide, are dispersed as less informative and disjointed pieces across various datasets, all pertaining to one single patient. So the circles with different colors represent knowledge fragments related to phenotypes and diagnostic expertise of pathologists. So the fragment nature of pathology knowledge hinders its suitability for computational analysis, thereby preventing artificial intelligence methods from fully leveraging the expertise encapsulated in pathology data. In view of this, the motivation of my research is to make pathology knowledge in multimodal pathology data more accessible, organized, and usable for computational analysis in order to facilitate AI-based pathology practice. So as illustrated before, the pathology knowledge are hidden within and fragmented across images and text. So the problem is how to represent the meaning of such knowledge in a machine understandable way in order to make it accessible and computable. We think about graph. So compare with natural language, an image graph is more structured form and has been widely used in representing biological knowledge, including pathway, protein functions, drug interactions. Inspired by this, I studied the graph representation of pathology knowledge. The outcome of my research is graph-based knowledge representation method named the PathoGraph. It consists of 3 graph definitions, and each representing different aspects of pathology, including pathology entity, pathology phenotype, and pathology diagnosis. I will illustrate the graph one by one. So pathology entity graph aims to represent the types and the morphological characteristic of pathological entities across biological scales. So it consists of 3 types of nodes: pathological entity, pathological feature, and a quantitative parameter. So the pathological entity is defined as biological structures that constitute disease tissues, which can be observed microscopically on a pathological slide. The table 1 lists the several examples of pathology entity, including tumor tissue, tumor cell. You can say they can further divide it into secondary components, and there exists a hierarchical composition relationship among those entities. And pathological features refer to the characteristic of pathological entities that could change as disease progresses, including both morphological and functional traits. So table 2 lists the various features of tumor cells and their components, which often undergo changes as the tumor progresses. The quantitative parameter refers to the measurable quantities that can quantitatively assess the extent of changes in pathological features. So comparing to using descriptive terms such as significantly enlarged, pronounced, the parameters can describe the changes in a pathological feature more objectively. And table 3 lists several quantitative indicators. So based on these 3 fundamental elements, the definition of pathology entity graph is provided as follows. The above is a visual representation, and the below is a graph theory-based representation. So in simple words, it's A represents the pathology entity, and it could link to several components denoted as E, and each component could have several pathology features denoted by C, and every feature can have a quantitative metric that quantitatively measure, how this feature is normal or abnormal. Now it comes to the pathological phenotype graph. So the pathological phenotypes refer to specific changes that can be used to distinguish different pathological conditions and reflect the underlying nature of disease. So we categorize pathological phenotypes into 3 types: single cell, multi-cell, and the quantitative phenotypic indicator. For each of these 3 types, we propose a corresponding graph structure. The single cell phenotype refer to the phenotypic manifestation observed in an individual cell, which may include changes in cell morphology. And in table 4 lists several examples, such as rhabdoid cell, tumor giant cell, tumor cell with nuclear groove. And the key to objectively characterizing such a phenotype is to identify the cellular components that have undergone pathological alterations, specify their pathological features, and quantitatively describe the extent of changes. So, in view of this, we provide a definition for a single cell phenotype graph as follows. So in simple words, a node will represent such phenotype, and it will link to the corresponding pathological entity graph, which describes the entity's characteristics as well as its composition. Multi-cell phenotype refer to phenotypic manifestation composed of several cells and other entities such as tissues, biomolecules, or anatomic structures. So the characteristics of this phenotype including not only the phenotypic features of all the composing entities, but also the spatial arrangement and the dynamic behaviors among the group of entities. The table 5 lists some of the multi-cell phenotypes. And so we define the multi-cell phenotype graph as follows. In simple words, that there's a node representing a multi-cell phenotype, and we represent it by specifying its components. And those components are linked by their spatial arrangement relationships or behaviors relationships. So quantitative phenotypic indicators are widely used in pathology reports to reduce the inter-observer variability and ensure reproducibility in diagnosis. Table 6 lists the sum of the indicators such as tumor stroma ratio, tumor infiltrating lymphocytes. So this is basically like you detect the several features and use sort of like a mathematical function to determine like the values that could quantitatively assess how a phenotype is abnormal. So based on that, we define a quantitative indicator graph by specifying which quantitative parameters are involved in this indicator and link them to the value of this indicator by a mathematical formula. So here comes the pathology diagnosis graph. It's a bit complicated, but it's defined like it's modeled by using several elements. The diagnostic items, which is the key data elements of pathology reports to which pathologists should deliver definitive diagnostic outcomes, such as grading of tumor cells or TIM staging. So in order to get the diagnostic result of diagnostic item, a pathologist should develop a diagnosis process, which could be divided into several stages. And then at the initial stage, he or she would obtain several phenotypes to rule in and rule out multiple diagnostic possibilities, and then get a very broad and non-specific diagnostic result. In the remaining stages, the pathologist would involve more phenotypes to narrow down the range of diagnostic results and until they get the most specific one. So we define a pathology diagnosis graph to represent such diagnostic approach. So to standardize the creation of a pathograph representation, we further develop pathograph into a markup language based on web ontology language, known as the pathology markup language. So in Patho, nodes of pathograph are implemented as either OWL classes or data properties, while edges are represented using object properties. So this approach allows pathograph representation to be instantiated via pathograph elements and transforming the graph representation into a standardized and machine-readable documents. We have applied a pathograph to represent the numerous phenotypes and diagnostic approaches, but due to the time limit, I'll just skip this part. In order to demonstrate the computational use of pathograph, we have performed a series of technical validations. First, we have developed an automatic construction pipeline of pathology entity graph, which has a pathology image patch as an input. And the first segment the tumor cells, nucleus, and calculate their morphological parameters, and then organize them into a pathograph, and finally output a pathoml documents. This demonstrated the feasibility of automatically constructing large-scale pathograph resources. Furthermore, we choose a patch-based subtyping as the learning task, to examine whether pathograph could improve deep learning-based computational pathology models. The model that incorporates the pathograph demonstrated superior performance, suggesting that pathograph representation can indeed provide performance gains for downstream computational pathology tasks. To further establish the pathograph's clinical relevance, we have developed several illustrative use cases demonstrating how pathograph can support a quantitative and traceable assessment of real-world diagnostic scenarios, which include the workflow of quantitative analysis of HER2 expression. I just noticed that the time, we have plenty of time, so I will go into detail. So this is like we first use the pathoml to represent the phenotype in IHC slide in the left, and then we can in order to have, this is a breast cancer image, and we represent the protein expression in different cells in specific regions using pathograph, and we can search the related features with a HER2 status by using simple Sparkle query, and then calculate those queries based on the results to facilitate a quantitative analysis of HER2 expression. And on the right is the same workflow to analyze the tumor infiltrating lymphocytes. Okay, so we have written 2 papers for this project. One has been published in Nature Scientific Data. The other one is also submitted to Nature Scientific Data and is currently under the second round of revision. All of the code has been made publicly available, and along with a PathoGraph data set, which is constructed using the automatic pipeline we have developed. We have plenty of time left. How about just go back to the part I skipped to introduce more about the pathograph representation of this phenotype. So these are several example use of pathograph to illustrate how pathograph represent the phenotypes and diagnostic approaches. This is the rhabdoid cell. And in order to represent in pathograph, we can for each, this is a cytoplasmic phenotype. And this cell is, according to pathologist description, this is compared to the normal cell. This is large cells with eosinophilic cytoplasm, and their nuclei are irregular shaped. Their nuclei are irregular shaped and eccentric with prominent nucleolus. So in order to describe this phenotype, we first create a pathologic entity named the rhabdoid cell, and as well as several other instances referring to its components. And for each of the pathological feature, such as large, irregular shape, eccentric, we create an instance of a pathological feature. For example, in order to describe the large, we can create a large instance and link it with a quantification instance, which gives the size of this cell. And for irregularly shaped, we can calculate the roundness of this cell to objectively characterize, how irregularly shaped this cell is. And to standardize the terms used to denote the large, irregular shape and rhabdoid cell, each of the instance has a cross-reference to the ontological terms. For example, we use the PATO to standardize the representation of the pathological features. And this is the representation of alveolar pattern, which is a multi-cell phenotype. We can, for the components of capillary tumor as well as their secondary components, the cellular components, we can create all instances to refer to these elements and link them together to represent the spatial pattern of this phenotype. And here is a representation of the diagnostic subtyping process for endocervical adenocarcinoma. By representing the process in PathoGraph, we can first, we can divide this diagnostic approaches into several steps. The first step, the pathologist will detect the granular patterns in the middle magnification, and he can get the general diagnosis that this patient is a adenocarcinoma. Furthermore, he can dive into the glandular patterns and detect the more granular phenotypes that further support this patient is a HPV-A patient, is a HPV-associated carcinoma. And finally, along with the quantitative metric of the percentage of tumor having cells with mucinal cytoplasms, he can finally give a conclusion that this patient is a HPV-A usual type. So this is a example representation of how pathologists diagnose a patient. So a little more about the implication of this work. So we envision that by using PathoGraph, we can represent all the knowledge across different modalities into a structure and a unified format. And by applying the nowadays AI pathology tools and models, those pathology knowledge elements could be automatically extracted and organized into PathoGraph, so that it allow us to generate large-scale PathoGraph resources. And based on that resources, it could be like how it could be feasible to develop the graph-based foundational models. And I think that the graph structure, one of the biggest advantages for graph compared to text and images, graph is more interpretable. Each node is an exact concept. So when we use that GN to give a prediction, you can always give like a subgraph with each node correspond to an exact concept. But when you use like a text and image models, as a graph. So I think that this work is mainly like allow us to organize all the information in graph structure and facilitate the graph neural network-based reasoning and interpretability in the AI practice in pathology. Thank you very much.
So what framework did you use for creating the pipeline that you process the pieces in?
You mean the automatic construction pipeline?
Yeah.
So what do you mean by framework?
Did you use like an open source tool, or did you create your own? Was it written in
Yes,
Python? Was it written in C? I mean,
we have applied several open source tools. I can explain in detail. Like the first step that this step is mainly segment tumors and the nucleus in this image. And for tumor segmentation, we use biomedical parse. This is a powerful segmentation tool mainly for tumor tissues. And for the nucleus segmentation, we use CellVit. It's a nucleus segmentation tool. And then we can determine their part-whole relationships by aligning their coordinates, the tumor segmentation coordinates, and the nucleus coordinates to determine whether this nucleus belongs to this tumor, and so that we can construct their part-whole relationships. And for each nucleus, because we have this segmentation, we can calculate the different morphological parameters, shape factor, roundness, size, etc. And when we get all this information, we can use the OWL related or graph, like a graph-based Python library to construct this PathoGraph, because like the part-whole relationship will be implemented as edge, and the segmented tumor tissues and the nucleus will be implemented as nodes, and then we can get the PathoGraph, and finally we can just use the OWL related Python library to generate a PathoML documents as the output.
Okay, so the output is the PathML.
Yes, yes, PathoGraph in PathML format.
Okay, and where'd you get the data set that you
We use the public available data set, which is called BRACS. It's a breast cancer data set. It's mainly an image patch with a breast cancer subtypes.
And does it come with pathologist comments on the images, or is it just the images?
There are images, and the annotations are the subtypes names.
Okay.
But there's no long sentences of these textual descriptions.
Okay.
Mm-hmm.
If you have two pathologies that are perhaps visually similar with only a minor distinction between them, are you able to capture in the output some sort of probability of the system thinks it's this one, but this other pathology could still be a high probability?
Could you? I'm sorry. Forgive my English. Could you really say? Yeah.
So you presented this as a very clear. You identify and relate everything to these nodes that then tell you the specific pathology. Presumably, there might be pathologies that share many nodes or look similar, but only have minor visual distinctions between them.
Okay. So you're saying that they have like a minor morphological difference between two phenotypes.
Yes.
Mm-hmm.
Yes. Does your system output any sort of confidence for its prediction or estimation?
No, not yet. So my method is mainly organize this, represent the information in the image in a graph structure format. So it's a
Show the, like which nodes it hits.
okay, yes, a node represents okay which cells are included, which tissue, and their relationships, and their describe their morphology by providing several morphological parameters, the numbers and values of their morphological parameters. But so the end result is a graph representation, but there is no prediction. But if you want to like, you can use this, or you can use it as an input in a graph neural network to get the prediction.
Sure.
And theoretically, if your graph neural network has like some SAG, like you know that a graph neural network has an interpretability module, right? So you can get like a multi-hop interpretability to explain, okay, why I have this prediction because I
What other ones?
pay attention to these and that nodes. And one of the advantages are these nodes like correspond to exact cell and tissue in the image. So it's more interpretable.
Do your nodes have like a strength associated with them for like this node is definitely part of this graph versus this node is like maybe part of the graph?
No, it's not.
Yeah.
No, they're just like they have exact relationship, but the
Okay.
This
So, first of all, I'm so surprised about your English. Because people, get all the education from China. It's hard to know that, right? Without he tells us.
yeah, thanks to the Hollywood films, I learned English mainly by watching Hollywood films.
Okay.
Yeah.
I have some questions on these slides. Like this slide, you have here two blocks, A and B, right?
Yes.
And then on the B, on the A, you have 3 steps. So what I'm wondering is, what is the graph? That is the whole block, or just the step 2?
Just step 2. The home block, the block A represents the construction pipeline for the pathology entity graph. And
just the way you get the graph.
yes, and the step 2, the output of the step 2 is the constructed graph. And the block B represents shows what this graph looks like. Like because in this is just an example. So I got the tumor, I got the nucleus, I got the morphological characteristics related to the cell. So when I constructed a pathograph, tumor nucleus and the features as well as the morphological parameters are treated as nodes. And there are, because when I segmented it, I have their bounding blocks and the segmentation coordinates. So I use this information as the data properties for the nodes. So block B is basically illustrated how, okay, what this graph looks like. What is nodes and what is edges.
Yeah, I understand. Because your title is the AI graph. So does that graph is completely, come out by the program?
Yes, it's completely.
There's no menu,
No. This because one of the reviewers pointed out that's a major issue for my initial version of paper is that he says that okay, he's fascinated by these figures, but they are all manual construction, like pathograph representation. He's wondering, okay, whether it's feasible to like construct automatically pathograph. So I added this like a modification in the second paper. Like we actually developed a automatic construction pipeline to generate a pathograph in an automatic way.
The one follow that one. Is that a graph is 3D or 3D or multi?
Still, your question is still with this page?
That graph, can you only construct graph or 3D or higher D? 2D, this is 2D. If 3D, like in a 3D
I guess.
body space. Dimensional.
I got it. It's just,
Yeah, yeah. I mean, what you can do is two-dimensional graph or 3D dimensional or multiple dimensional. Yeah, or high dimensional. Yeah.
I don't think, because that the graph is just like basically a OW document.
Yeah.
That so I'm not so sure about if this could be considered as like 2D or 3D, because from from my point of view, it's just like a different many nodes, and there are edges linking them together. So I'm not so sure how to like define
Like
it's
you talked
2D
about
or
the
3D.
coordinates, but they're just in like XY coordinates of the
Oh.
relationship. He's saying, could you go XYZ like and show the relationships between
The coordinates is like the information we detected from the image, and its coordinates will be treated as like a data property for a certain node. Like we get a segmentation coordinates. This is obtained from a 2D image, an image patch, and it's related to one cell, and it refers to this cell position in that image, and we just add this information in that node as a data property.
Okay.
Yeah.
Okay. Well, what I meant is, I'm imagining if you use the multiple D, that will avoid, the cross of all those lines. So this line, because every node has limited line, then if you have more lines or the more reactions from the other nodes, you probably got a lot of cross sections. So then if you use the high dimensional graph, that will avoid that cross sections. But anyways, this is very good.
Thank you.
We had a question in the YouTube chat. Have you talked to any practicing oncologists to get their feedback?
Sure. This project, I mean, was guided and mentored by Mayo Clinic pathologists, and all elements are like determined by what knowledge elements should be involved in the pathology entity graph, phenotype graph, diagnosis graph, are determined by Mayo Clinic pathologists. So,
I have new questions. So from this graph, how do I know it is the input nodes and the output node or nodes?
input nodes. The input is basically like the input nodes. What do you mean by like input nodes?
Input nodes,
Like
such as you get the image from whatever machines, right? That's basically is a histology, math. And then you got a lot of computations, and then got a result. Okay,
Yes.
this is the result. This is output. So how do we know without read any text? Then you immediately figure out, oh, this is input, that is output.
Because the input is like starting from the image, and we just extract the information from the image, and we store and organize those information in the like a predefined pathograph structure. So yeah, it's just like we develop some code and put this information in that node, put that information in that node, and develop an edge in between. So just a simple code.
Does the initial or the raw image included in that node?
Yes. Yes. The raw image would be included in that node because let's go back to the PathoML structure. Just in the markup language we developed for PathoGraph, we have several classes, indicative data modalities. Like for each image, like we will have a class referring to the raw image from which we extract the information and create the pathograph. So there will be a node storing the metadata of that image, including patient ID or the slide ID or the format. And that would be a node and linking with all the semantic nodes, which represent the information containing in that image. So yes, the image would be one of the nodes. Yeah, and in the downstream, the computational pathology, prediction, for more details about this slide is that we implement a graph neural network. It's actually a graph neural network plus SAG pooling. It's a attention mechanism. So we first develop, we use this model and we use two graphs. One is PathoGraph. The other is like a traditionally image patch graph. So when you input the PathoGraph, you have the raw image. You have the different cell nodes. Not only has the cell patches, like a small region of that cells in the original image, you also have, okay, what kind of cell? And whether this is a tumor cell, and if this is a tumor cell, okay, what tumor it belongs to, all sort of semantic information. But for the other graph, it's just the image patch constructed based on there's nearest neighboring approach. So we use the same model to embed in the pathograph and the image patch graph and compare their performance for the learning task, which is a patch-based subtyping result. Subtyping, basically that you input a patch, you predict the subtype of this patch, whether it's a breast cancer or other cancer types. And as you can see from the performance figure, that the model using pathograph outperforms the one used the patch graph. And I think that it is due to that pathograph contains not only the raw image features as well as the semantic features, which contributes to the model's performance compared to a purely image patch graph.
In order to use your software, this is kind of software, right? The image processing software.
Yes, for the construction pipeline.
Suppose I have a raw image sets and then run your program.
Mm-hmm.
And how many additional information I should type in, or
Well,
just
maybe,
read the program, read the image?
For now, the information you should specify is that what kind of tissues you want to segment. If the input is a tumor patches, so you want to segment tumors, you want to segment different cell, you need to specify what kind of a pathology entities you want to involve in the pathograph representations. Because it is because that this is how the biomed parse, which tool we use for segmentation, that is designed, because biomed parse needs to specify the types of entities you want it to segment. So you just gave the types of entities you want to extract and organize it into a pathology graph. You type it and then you can leave all the rest.
So can this software, analyze the multiple type of image, or just the specified one type?
For now, it only applies to HE slide.
What?
Hemotoxin eosin slides.
Okay. And because for example, when you diagnose the cancer, right? Some slides maybe not exactly the cancer, maybe inflammation, maybe benign.
Yes.
So how do you have a way to distinguish all those stuff?
Not yet.
Okay.
Yeah, because like this construction pipeline is a very initial one. Applies to limited image modalities and limited a number of like pathology entity types. Like if you want to build a constructed pipeline that represent like different neoplastic disease and applies to different modalities and represent all these information in PathoGraph, that this should we have a long way to go.
Right.
Yeah, because in pathology, there's like in the field of pathology, we don't have the segment everything. In order to do that, we need to develop a segment everything
I see.
at the first place.
Okay, thank you.
Thank you. And little complaint that the researchers in pathology, especially like the imaging, those people escape from like they escape from this like segment everything topic, because like for the natural image, it's easy to segment those objects because in natural image, the number of objects in the image are limited compared with the pathology, compared with the HE slides. But for example, in HE slides, the number of slides could be over millions.
Right.
The number of tissues could be like 100. The number of like a bigger tissues could be like 100. So it would be like very hard to develop segment everything for pathology images.
Right.
But still, it's very it's necessary.
Thank you.
All right, can we give everyone, or everyone, please give Dr. Liu a hand?
Okay.